Deep beneath your feet, buried in rock layers 50 million years old, lies a mystery that could shatter everything you believe about human uniqueness. Scientists have discovered chemical signatures in ancient sediments that look disturbingly familiar. They match the fingerprints our industrial civilization is leaving right now. What if we are not the first? What if intelligence has risen before, built cities, changed the climate, and vanished without a trace? We will journey through 26 pieces of evidence that suggest Earth may have hosted previous civilizations. Prepare yourselves. We begin. Your city will be gone in 10,000 years. Every skyscraper, every highway, every monument we consider permanent will crumble into dust while Earth barely notices. This isn't speculation. We know exactly how fast our civilization disappears because we can see it happening right now. In the abandoned zones around Chernobyl, nature has already begun erasing 30 years of human presence. Vines crack concrete, trees split foundations, metal rusts into orange powder that washes away with the next rain. Think of concrete like a sandcastle. It feels solid when you build it, but time is an endless tide. Freeze and thaw cycles work like hammers, striking millions of times each year. Chemical reactions turn steel into iron oxide. Even our most durable materials follow the same rule that governs everything in nature. Order becomes chaos, structure becomes dust. The only human artifacts likely to survive beyond 1 million years are the simplest ones: stone tools, pottery shards, plastic fragments scattered in sediment layers. Everything else that defines our technological civilization will vanish completely, leaving almost no trace that we ever existed. But what fascinates scientists is this question: if our advanced civilization disappears so quickly, how would we ever detect evidence of a previous one? And that brings us to an even stranger realization. Human civilization occupies less than 1/100% of Earth's history. Imagine Earth's 4.5 billion year story compressed into a single day. Humans appear in the last second before midnight. Our entire industrial age, from the steam engine to smartphones, happens in the final millisecond. We are geological newcomers who have been here for such a brief moment that our presence barely registers in the rock record. This creates what scientists call the detection problem. When you look at rock layers, each inch represents thousands or even millions of years of compressed time. A civilization that lasted 10,000 years would appear as a line thinner than paper between massive stone chapters. Most sediment cores skip right over such brief intervals. Consider this unsettling fact. If an industrial civilization existed 60 million years ago and lasted twice as long as ours has so far, we would need incredible luck to find any trace of it. The odds are like searching for a single page torn from a book and scattered across a continent. You might look in all the right places and still find nothing. But here's what changes the game entirely. Industrial civilizations don't just build things that decay. They change the chemistry of the entire planet in ways that can persist for millions of years. They leave signatures written in the atomic structure of rocks themselves, which leads us to examine what those signatures might look like. We produce 300 million tons of plastic every single year. Most people think plastic pollution is forever, but that's wrong. Plastic breaks down relatively quickly on geological timescales. Heat, sunlight, and chemical reactions tear apart those long molecular chains within thousands of years, not millions. The plastic bottles littering our oceans today will be gone long before the next ice age arrives. However, plastic doesn't just disappear, it transforms. As those molecular chains break apart, they release specific chemicals that become incorporated into sediment. Scientists can detect these chemical markers even when the original plastic has completely vanished. It's like finding the ghost of a molecule, a chemical fingerprint that proves something artificial was once there. Think of it like perfume lingering in a room. The person wearing it has left, but you can still detect their presence through molecules floating in the air. Plastic leaves similar molecular traces in rock layers, creating what geologists call a synthetic signature. This signature includes compounds that simply cannot form through natural processes. The most persistent markers come from additives mixed into plastic during manufacturing. Flame retardants, UV stabilizers, and plasticizers contain rare combinations of elements that would never occur naturally. These compounds get incorporated into marine sediments when plastic debris settles on the ocean floor. But plastic is just one example of how industrial activity leaves chemical traces. There are dozens of other signatures we're creating right now that could persist for millions of years, and some of the most revealing signatures come from something we never intended to leave behind. Hidden in ancient rock layers are carbon signatures that don't make sense. Scientists drilling ice cores and sediment samples occasionally find layers where the carbon chemistry suddenly shifts in dramatic, unexpected ways. The isotope ratios change rapidly, indicating that massive amounts of carbon were released into the atmosphere over very short geological periods. Natural processes like volcanic eruptions or forest fires can cause carbon spikes, but some of these ancient anomalies look different. They look industrial. When we burn fossil fuels, we release carbon that has a specific isotopic signature. Coal, oil, and natural gas formed from ancient organic matter, so they contain lighter carbon isotopes compared to the carbon in living plants. This creates a measurable shift in atmospheric chemistry that gets recorded in tree rings, ice cores, and ocean sediments. Picture carbon isotopes like fingerprints. Each source has a unique pattern. Volcanic carbon has one signature. Forest fire carbon has another. Industrial carbon from burning fossil fuels has a third, distinctly different pattern. When scientists find this industrial pattern in rock layers millions of years old, it suggests something was burning fossil fuels back then. The most puzzling examples come from sediment cores in the deep ocean. Several layers show rapid carbon chemistry changes that happened over periods of just a few thousand years. That's extremely fast in geological terms, suggesting sudden, massive carbon releases that overwhelmed natural cycles. These carbon spikes are often accompanied by other chemical changes that make them even more intriguing. Our oceans are becoming more acidic as they absorb carbon dioxide from fossil fuel burning. This ocean acidification process is happening at a rate that alarms marine biologists. The pH of seawater is dropping measurably every year, dissolving coral reefs and disrupting the entire marine food chain. We can track this acidification in real time using instruments placed throughout the world's oceans. But when scientists examine ancient sediment layers, they find evidence that oceans have acidified rapidly several times in Earth's deep past. The chemical signatures are unmistakable. Calcium carbonate shells dissolve. Marine ecosystems collapse. The fossil record shows mass extinctions that coincide perfectly with these acidification events. Natural processes can acidify oceans, but most happen very slowly over millions of years. Volcanic activity or asteroid impacts can cause faster changes, but they leave other obvious traces. Some ancient acidification events have no clear natural explanation. Think of ocean chemistry like a massive buffering system. It takes enormous inputs of carbon dioxide to overcome the ocean's natural ability to maintain stable pH. When you find rapid acidification in the geological record, something was pumping tremendous amounts of carbon into the atmosphere very quickly. The most mysterious acidification events are those that show multiple rapid pulses, like someone was turning a massive carbon source on and off repeatedly. This pattern suggests control and management rather than a single catastrophic natural event. These chemical signatures become even more interesting when you examine what happened to certain elements during these ancient events. Every industrial process changes the isotopic signature of elements in predictable ways. When we smelt metals, refine petroleum, or manufacture chemicals, we're essentially sorting atoms by weight. Lighter isotopes behave slightly differently than heavier ones during chemical reactions. This creates distinctive isotopic patterns that persist long after the original industrial activity has ended. Lead isotopes provide the clearest example. When ancient civilizations smelted lead ores, they unknowingly created specific lead isotope ratios that are completely different from natural background levels. Scientists can detect these artificial lead signatures in ice cores and sediment layers, providing direct evidence of metal production thousands of years ago. The same principle applies to other elements. Copper, zinc, silver, and mercury all show isotopic fingerprints from industrial processing. These signatures are like atomic serial numbers that identify human activity even when all physical artifacts have disappeared. Think of isotopes like identical twins with slightly different weights. When you put them through industrial processes, the lighter twin moves a bit faster than the heavier one. This separation creates patterns that nature rarely produces on its own. What makes this evidence so compelling is its persistence. Isotopic signatures can survive for millions of years because they're literally built into the atomic structure of sediments. Unlike artifacts that rust and decay, these chemical fingerprints remain readable across geological time. Some of the most dramatic isotopic anomalies in Earth's history coincide with mysterious mass extinction events. 5 times in Earth's history, more than 75% of all species have suddenly vanished. These mass extinctions have obvious natural causes. Asteroid impacts, massive volcanic eruptions, or dramatic climate changes can explain most of the devastation. But when scientists examine the details of how these extinctions unfolded, some patterns look disturbingly artificial. The most puzzling aspect is selectivity. Natural disasters typically kill randomly, but some ancient extinctions show strange biases. Large animals disappear while smaller ones survive. Marine species in shallow waters die, while deep ocean creatures thrive. Species dependent on complex food webs vanish, while simpler organisms persist. This selective pressure looks remarkably similar to what's happening during our current extinction event. We're not killing species randomly. We're systematically destroying habitats, overharvesting resources, and disrupting ecological relationships. The result is a highly selective extinction pattern that preferentially eliminates large, complex, and specialized species. Think of natural extinction like a hurricane that destroys everything in its path. Industrial extinction is more like urban development that carefully removes certain species while leaving others untouched. The patterns are completely different and easily recognizable. Several ancient mass extinctions show this selective signature, combined with rapid environmental changes that look industrial rather than natural. The timing is also suspicious. These extinctions often happen much faster than natural climate change can explain. But the most convincing evidence comes from examining what disappeared during these ancient events. Every smartphone contains 17 different rare earth elements. These elements, with names like neodymium, dysprosium, and terbium, are essential for modern technology. They make magnets stronger, screens brighter, and batteries more efficient. Without rare earths, we couldn't build computers, electric motors, or renewable energy systems. Here's the problem. These elements are genuinely rare. There are only a few dozen economically viable deposits scattered across the entire planet. Once we extract and use these materials, they don't disappear, but they get dispersed and diluted beyond practical recovery. We're essentially mining our way through a finite resource that took billions of years to concentrate. What fascinates geologists is that several ancient sediment layers show unusual depletion patterns for rare earth elements. These layers have lower concentrations than would be expected from natural processes. Something was extracting and redistributing these materials millions of years ago. Think of rare earth mining like harvesting honey from wild beehives. The first civilization to discover these deposits would have easy access to concentrated ores. But after intensive extraction, future civilizations would find only scattered, low-grade deposits that are much harder to exploit. This creates what scientists call the resource bottleneck. If a technological civilization depletes critical mineral resources, it becomes much harder for the next civilization to reach advanced industrial levels. They would need to develop more sophisticated extraction and recycling technologies just to achieve what their predecessors accomplished easily. The geological evidence suggests this bottleneck may have operated before. It takes 100 million years for Earth to produce a new generation of fossil fuels. Coal, oil, and natural gas form through incredibly slow geological processes. Organic matter must be buried under specific conditions, heated to precise temperatures, and compressed for millions of years. The fossil fuels we're burning today began forming when dinosaurs ruled the Earth. This creates a fascinating detection opportunity. If a previous industrial civilization burned through Earth's fossil fuel reserves, there would be a gap in the geological record. Layers that should contain coal or oil deposits would be mysteriously empty or depleted. Several sedimentary basins around the world show exactly this pattern. Rock formations that have all the right conditions for fossil fuel formation, but contain far less organic carbon than geologists would expect. These missing deposits could represent fossil fuels that were extracted and burned millions of years ago. Think of fossil fuel formation like wine aging in a cellar. Each geological layer represents a different vintage, slowly developing over millions of years. If you found empty spaces where certain vintages should be, you'd know someone had already harvested them. The evidence becomes even more compelling when you consider the chemistry of what happened to these missing deposits. Burning massive quantities of fossil fuels would leave specific chemical signatures throughout the environment. Those signatures would persist much longer than the civilization that created them. Our most advanced technologies leave the smallest traces. Bronze axes survive in museum collections after 3,000 years. Stone tools last for millions of years, but silicon computer chips crumble into powder within decades. Fiber optic cables degrade faster than wooden handles. The more sophisticated our technology becomes, the less likely it is to survive as recognizable artifacts. This creates a strange archaeological paradox. The most advanced civilizations leave the fewest physical traces. If we discovered the ruins of an ancient city today, we would find pottery, metal tools, and stone foundations. We would never find computer processors, plastic components, or electronic devices, even if they had been the most important technologies that civilization used. Advanced materials like carbon fiber composites, rare earth magnets, and synthetic polymers are designed to be lightweight and efficient, which makes them inherently fragile over geological time. They oxidize, decompose, or dissolve much faster than crude materials like iron and stone. Think of technology preservation like building materials for a house. Concrete blocks and steel beams will outlast high-tech insulation and sophisticated electronics by millions of years. Archaeologists of the future would find evidence of our construction methods, but miss most of our actual technology. This means that if we want to detect evidence of previous technological civilizations, we cannot rely on finding their artifacts. We need to look for more subtle signatures that advanced technology creates in the environment, and some of those signatures are written in the deepest layers of Earth itself. Ice cores from Antarctica contain a record of Earth's atmosphere going back 800,000 years. Every year, snow falls on the polar ice caps and compresses into ice layers, trapping tiny bubbles of ancient air. Scientists can extract these bubbles and measure the exact composition of the atmosphere from hundreds of thousands of years ago. It's like having a chemical diary of Earth's climate history. The ice core record shows natural cycles of carbon dioxide, methane, and other greenhouse gases. These cycles correspond to ice ages, volcanic eruptions, and other known climate events. But scattered throughout this record are brief spikes and anomalies that don't match any natural pattern. Some of these anomalies look suspiciously similar to our current industrial emissions. Rapid increases in carbon dioxide and methane, followed by strange chemical signatures that suggest industrial activity. The timing and magnitude of these spikes cannot be explained by volcanism, forest fires, or other natural processes. Think of ice cores like tree rings, but for the entire planet's atmosphere. Each layer contains chemical information that reveals what was happening in the environment when that ice formed. Unusual chemical combinations stand out like foreign words written in a familiar language. The most intriguing anomalies are those that show multiple industrial signatures occurring simultaneously. Carbon dioxide spikes, accompanied by sulfur compounds, nitrous oxides, and trace metals that suggest coordinated industrial activity rather than random natural events. But ice cores only go back 800,000 years, which is recent in geological terms. A civilization lasting 10,000 years would occupy a sediment layer thinner than a sheet of paper. Ocean sediments accumulate incredibly slowly, typically less than an inch per 1,000 years. This means that entire civilizations can be compressed into layers so thin that standard geological sampling techniques skip right over them. Most sediment cores are taken at intervals of several inches, which could easily miss brief industrial periods. Scientists face what they call the sampling resolution problem. The tools and methods designed to study geological processes over millions of years are poorly suited to detect events lasting only thousands of years. It's like trying to find a needle in a haystack, but the needle is smaller than the spaces between the hay. However, there are locations where sediment accumulates much faster. River deltas, coastal margins, and certain deep ocean basins can preserve much higher resolution records. In these special locations, a 10,000-year civilization might occupy a measurable layer with detectable chemical signatures. Think of sediment layers like pages in a book about Earth's history. Most pages cover millions of years, so brief civilizations are like single sentences scattered across thousands of pages. You need to know exactly where to look, and you need sampling techniques designed to catch these brief intervals. Recent advances in analytical chemistry allow scientists to detect industrial signatures even in very thin sediment layers. They can identify synthetic compounds, isotopic anomalies, and chemical combinations that indicate technological activity. Some of the most promising evidence comes from sediments that shouldn't contain certain elements at all. Nuclear technology leaves signatures that persist for millions of years. When we split atoms in nuclear reactors or weapons tests, we create isotopes that don't exist naturally on Earth. These artificial isotopes have distinctive decay signatures that can be detected long after the original radioactive material has decayed to safe levels. They're like atomic fingerprints that prove nuclear technology was once active. The most persistent nuclear signatures come from plutonium production and uranium enrichment. These processes create specific ratios of uranium and plutonium isotopes that never occur in nature. Even after millions of years, scientists can detect traces of these artificial isotopes in sediment layers. Nuclear accidents and weapons testing also leave characteristic patterns. The Chernobyl disaster created a global fallout signature that will remain detectable for thousands of years. Nuclear weapons tests from the 1950s created artificial isotopes that are now incorporated into tree rings, ice cores, and sediments worldwide. Think of artificial isotopes like radioactive signatures written in atomic ink. They fade over time as the isotopes decay, but they follow predictable mathematical patterns that allow scientists to trace them back to their original source and date of creation. What makes nuclear signatures particularly valuable for detecting ancient civilizations is their uniqueness. There are no natural processes that can create these specific isotope combinations. Finding them in ancient sediments would be definitive proof of technological activity. Several deep ocean sediment cores contain unexplained isotopic anomalies that could represent ancient nuclear signatures. 2.5 billion years ago, cyanobacteria polluted Earth's atmosphere with a deadly poison called oxygen. This mass poisoning event, known as the Great Oxidation Event, killed most life on Earth. The toxic oxygen gas reacted with everything it touched, causing what scientists call the first global pollution crisis. It took millions of years for new life forms to evolve that could tolerate this poisonous atmosphere. From our perspective, oxygen seems natural and necessary, but that's only because we evolved to breathe it. The original atmosphere contained almost no oxygen, and most early life forms found it as toxic as we would find hydrogen sulfide or chlorine gas. This precedent shows that intelligence and technology aren't required to cause global environmental catastrophes. Simple organisms can completely transform planetary chemistry through their biological processes. If bacteria can poison the entire atmosphere, imagine what an industrial civilization might accomplish. Think of the Great Oxidation Event like a dress rehearsal for industrial pollution. It demonstrates that Earth's environment can be radically altered by the byproducts of biological activity. The same principles apply to technological activity, but the timescales are much faster. What makes this precedent particularly relevant is that it left permanent chemical signatures in rock layers worldwide. The oxidation event created distinctive iron formations and sulfur isotope signatures that geologists can still identify billions of years later. If organisms can leave such clear chemical fingerprints, technological civilizations should leave even more obvious traces. At the bottom of the ocean, in sediment layers 50 million years old, lie mysterious zones where nothing lived. These ancient dead zones appear as dark bands in sediment cores, completely devoid of fossils, organic matter, or any signs of life. They represent periods when vast areas of the ocean became so toxic that no organisms could survive there. The chemistry of these layers suggests extreme pollution that overwhelmed natural ocean systems. Most dead zones form when excess nutrients cause massive algae blooms that consume all available oxygen. When the algae die and decompose, they create anoxic conditions that kill everything else. This process happens naturally in some environments, but the ancient dead zones are far more extensive and severe than anything natural processes typically create. The most puzzling aspect of these ancient dead zones is their geographic distribution. They don't follow patterns you would expect from natural causes like volcanic activity or climate change. Instead, they seem to cluster around continental margins and major river systems, exactly where you would expect industrial pollution to be most concentrated. Think of these dead zones like crime scenes preserved in rock. The evidence shows that something killed marine life across vast areas of the ocean, but the usual suspects, natural disasters, don't match the patterns of destruction. Chemical analysis of these dead zone sediments reveals synthetic organic compounds and metal concentrations that are difficult to explain through natural processes. The signatures suggest industrial runoff and chemical contamination on a scale that would require sophisticated manufacturing capabilities. But these ocean dead zones are just one piece of a much larger puzzle that becomes even more intriguing when you examine what happened on land during the same time periods. Copper should be randomly distributed throughout Earth's crust, but it isn't. When geologists map the locations of metal deposits around the world, they expect to find patterns that match natural geological processes. Volcanic activity, hydrothermal vents, and sedimentary processes create predictable distributions of metals based on chemistry and physics. But several elements show clustering patterns that don't match these natural processes. The most obvious anomaly involves metals essential for technology. Copper, tin, and zinc deposits often occur in combinations and concentrations that would be extremely useful for Bronze Age or industrial civilizations. It's as if someone had already identified and exploited the richest, most accessible ores, leaving behind depleted zones and scattered deposits. Archaeological evidence supports this interpretation for recent human activity. Ancient mining sites show clear evidence of selective extraction. Miners targeted the richest ores and left behind lower-grade materials. This creates distinctive geochemical signatures that persist long after the mining activity has ended. Think of metal distribution, like picking fruit from an orchard. The first harvesters take the largest, ripest fruit from the most accessible trees. Later, visitors find only smaller fruit in harder-to-reach locations. The pattern of what remains tells a story about who was there before. What makes this evidence particularly compelling is that some ancient depleted zones are far older than human civilization. Geological surveys reveal mining-like patterns in rock formations that date back millions of years. These patterns suggest systematic extraction of high-grade ores by unknown agents. The depletion patterns become even more suspicious when you examine how precisely they match the requirements for advanced metallurgy. The Great Pyramid of Giza is disappearing at a rate of 1 inch every 1,000 years. Even the most durable human constructions follow predictable decay curves. Stone monuments weather according to mathematical formulas based on precipitation, temperature cycles, and chemical erosion. Scientists can calculate exactly how long it would take for any structure to become unrecognizable. The results are sobering. Mount Rushmore will be unreadable in 500,000 years. The Great Wall of China will be invisible in 2 million years. Even structures built from the most durable materials available to human engineering will vanish completely within 10 million years. This creates what archaeologists call the monument paradox. If previous civilizations built structures comparable to our greatest achievements, we should occasionally find traces of their foundations or remnants of their materials. The absence of such evidence suggests either that no previous civilizations existed or that they built using materials and methods completely different from ours. Think of monument decay like erosion carving canyons from solid rock. The process is slow, but absolutely relentless. Every freeze-thaw cycle, every acid rainstorm, every seismic tremor contributes to the gradual dissolution of even the most massive structures. However, there are locations where unusually durable materials might survive much longer. Certain crystalline formations, synthetic diamonds, or engineered ceramics could potentially persist for hundreds of millions of years under the right conditions. Some geological formations show curious regularities that could represent the heavily weathered remains of artificial structures. But the most intriguing evidence comes from materials that shouldn't exist in nature at all. Hidden in ancient sediments are molecules that could never form naturally. Every chemical compound follows specific rules about how atoms can bond together. Natural processes create predictable molecular patterns based on temperature, pressure, and available elements. But industrial chemistry can force atoms into arrangements that would never occur without technological intervention. These synthetic molecules act like chemical fossils that prove artificial activity took place. Even after the original materials have decayed, their breakdown products retain distinctive molecular signatures. Scientists can identify these signatures using mass spectrometry and other analytical techniques, detecting artificial compounds at concentrations as low as parts per trillion. The most persistent synthetic signatures come from polymer chemistry. When plastics, synthetic fibers, and industrial chemicals break down, they leave behind specific molecular fragments that have no natural counterparts. These fragments can survive for millions of years in sediment layers, providing direct chemical evidence of technological activity. Think of synthetic molecules like artificial DNA. Each one carries information about the industrial processes that created it. The molecular structure reveals details about temperature, pressure, catalysts, and manufacturing methods that would be impossible to achieve without sophisticated technology. Recent advances in analytical chemistry have allowed scientists to detect these synthetic signatures in sediment cores dating back millions of years. Some ancient layers contain molecular patterns that closely resemble modern industrial byproducts, but with subtle differences that suggest different manufacturing processes. The implications become even more intriguing when these chemical signatures appear alongside biological markers that shouldn't exist either. DNA contains a record of every genetic modification that has ever occurred. Modern genetic engineering leaves distinctive traces in the genomes of modified organisms. Inserted genes, deleted sequences, and artificial regulatory elements create patterns that are clearly different from natural evolution. These biomarkers persist in the fossil record and can be detected even in ancient DNA samples. What surprises paleogeneticists is that some ancient DNA samples contain sequences that look suspiciously artificial. These sequences show evidence of precise editing, systematic modifications, and genetic combinations that are statistically unlikely to have occurred through natural mutation and selection. The most intriguing examples come from extinct species that show signs of rapid, coordinated genetic changes. Instead of gradual evolutionary adaptation, these organisms appear to have undergone sudden improvements in multiple traits simultaneously. This pattern is characteristic of intentional genetic engineering rather than natural selection. Think of genetic engineering like editing a book. Natural evolution makes random changes that are usually harmful, like typos that make sentences unreadable. Genetic engineering makes purposeful changes that improve the text, like a skilled editor correcting grammar and adding better vocabulary. Some ancient species show genetic modifications that would have required sophisticated understanding of molecular biology, improved disease resistance, enhanced metabolic efficiency, and optimized reproductive systems that appear suddenly in the fossil record without obvious evolutionary precursors. These biomarkers suggest that genetic engineering may have been practiced millions of years before humans developed the technology, which raises questions about who was doing the engineering and what happened to their civilization. Geologists have identified 23 distinct geological ages in Earth's history. Each geological age is defined by dramatic changes in rock layers, fossil assemblages, or chemical compositions that mark major transitions in Earth's development. Most of these transitions have clear natural causes like asteroid impacts, volcanic eruptions, or gradual climate shifts. But several geological boundaries show characteristics that closely resemble our current Anthropocene age: rapid environmental changes, mass extinctions with selective patterns, and chemical signatures that suggest technological activity. These proto-Anthropocene periods occurred at regular intervals throughout Earth's history. The timing is particularly suspicious. These rapid transition periods appear to follow a rough cycle, occurring approximately every 50 to 100 million years. This suggests a recurring pattern rather than random natural events. Something happens periodically that dramatically alters Earth's environment and biology. Think of Earth's geological history like a repeating musical composition. Most of the song follows natural rhythms and patterns, but certain movements include sudden crescendos and dramatic key changes that stand out from the background melody. The most detailed evidence comes from the Paleocene-Eocene thermal maximum, which occurred 56 million years ago. This period shows rapid global warming, ocean acidification, and mass extinction patterns that are remarkably similar to current human impacts. But it happened long before any known intelligent species existed on Earth. Chemical analysis of rocks from these periods reveals isotopic signatures, synthetic compounds, and metal distributions that are difficult to explain through natural processes alone. These recurring patterns suggest that the rise and fall of technological civilizations might be a regular feature of Earth's long-term evolution. Silicon solar panels leave distinctive geological signatures that persist for millions of years. When solar panels degrade, they don't simply disappear. The high-purity silicon, rare earth elements, and synthetic materials break down into characteristic chemical patterns. These breakdown products have specific isotopic signatures and molecular structures that are completely different from naturally occurring silicon compounds. The manufacturing process for solar cells also creates unique environmental signatures. Silicon purification requires enormous amounts of energy and produces distinctive chemical byproducts. These industrial processes leave traces in the atmosphere, groundwater, and surrounding sediments that can be detected long after the original manufacturing facilities have disappeared. Modern, renewable energy infrastructure represents a massive global deployment of rare earth elements, synthetic materials, and precision manufacturing. If a previous civilization had developed similar technologies, they would have left similar chemical fingerprints throughout the environment. Think of solar panel manufacturing like a massive chemistry experiment conducted across the entire planet. Every factory, every installation, every degraded panel contributes chemical signatures to the global environment that accumulate over time. Some ancient sediment layers show unusual concentrations of ultra-pure silicon and rare earth elements in combinations that closely resemble solar technology byproducts. These layers also contain synthetic compounds that are consistent with large-scale renewable energy manufacturing. The geographic distribution of these chemical signatures suggests coordinated global deployment, similar to how our current renewable energy transition is creating worldwide chemical markers. But renewable energy is just one type of technology that leaves persistent environmental traces. Evolution might be running the same experiment over and over again. Intelligence appears to be an inevitable outcome of evolutionary processes. Once nervous systems reach sufficient complexity, problem-solving abilities, tool use, and social cooperation emerge reliably across many different species. This suggests that technological civilizations might arise whenever conditions permit, following predictable developmental pathways. The recycling theory proposes that Earth periodically produces intelligent species that develop technology, alter the environment, and then disappear due to resource depletion or environmental collapse. After each civilization falls, Earth gradually recovers and begins the evolutionary cycle again with new species. This process could explain why geological evidence for previous civilizations is so subtle and scattered. Each civilization would exploit different resources, develop different technologies, and leave different types of environmental signatures. But they would all follow similar patterns of rapid development, environmental impact, and eventual collapse. Think of civilization development like successive generations of gardeners working the same plot of land. Each gardener plants different crops, uses different tools, and makes different mistakes. But they all follow similar patterns of soil cultivation, resource extraction, and environmental modification. The timescales involved make this recycling process almost invisible to individual civilizations. 50 million years is sufficient for most environmental damage to heal, new species to evolve, and fresh resource deposits to form. Each new civilization would inherit a planet that appears pristine and untouched. Archaeological evidence supports this recycling model. The fossil record shows repeated episodes of rapid brain evolution in different lineages, suggesting that intelligence develops multiple times independently, which raises the question of what we might be able to detect from space. Everything we launch into space eventually falls back to Earth. Satellites, space stations, and other orbital debris follow predictable decay patterns based on atmospheric drag, solar radiation, and gravitational perturbations. Most objects in low Earth orbit re-enter the atmosphere within decades or centuries, where they burn up and contribute their materials to global atmospheric chemistry. This creates a distinctive signature in atmospheric and sediment records. Space-grade materials like titanium alloys, specialized ceramics, and rare earth magnets have isotopic compositions that are different from terrestrial sources. When these materials burn up during re-entry, they create unique chemical signatures that get incorporated into global environmental records. A technologically advanced civilization would likely develop space technology and launch significant amounts of material into orbit. Even if their civilization collapsed, their orbital infrastructure would continue falling back to Earth for thousands of years afterward, creating a prolonged signature of artificial materials in environmental records. Think of orbital decay like a very slow rain of technological artifacts. Each re-entry event deposits tiny amounts of artificial materials into the atmosphere, where they mix with natural processes and eventually settle into sediment layers. Some ancient atmospheric chemistry records show unexplained spikes in rare metals and synthetic compounds that could represent orbital decay signatures from previous space programs. These spikes occur in clusters over thousands of years, exactly what you would expect from a civilization that had launched substantial infrastructure into orbit. The isotopic signatures of these materials are particularly intriguing because they show characteristics consistent with space manufacturing processes. But orbital debris is nothing compared to what intelligence itself might be doing to the universe. Intelligence creates intelligence in an accelerating spiral that might be unstoppable. Once a species develops language, tool use, and abstract reasoning, it begins modifying its own environment in ways that favor further intelligence development. Better tools require smarter users. Complex societies reward problem-solving abilities. Cultural evolution accelerates biological evolution toward greater cognitive capabilities. This creates a positive feedback loop that drives intelligence toward higher and higher levels of complexity. Each generation of intelligent beings creates challenges that require even more intelligence to solve, pushing cognitive evolution at accelerating rates. Human development follows this exact pattern. Our ancestors developed language, which enabled complex cooperation, which enabled tool development, which enabled agriculture, which enabled civilization, which enabled science, which enabled technology that augments our intelligence even further. Think of intelligence evolution like compound interest. Small improvements in cognitive ability generate larger improvements in technology, which create even larger improvements in cognitive enhancement in an ever-accelerating spiral towards superhuman capabilities. The mathematical models suggest that once this spiral begins, it becomes almost impossible to stop. Intelligence creates tools that make it more intelligent, which create better tools, which make it even more intelligent, in an explosive feedback loop. If this process is universal, then every planet that develops life will eventually produce intelligence that follows this same accelerating pattern. The spiral would continue until the intelligent species either transcends its planetary limitations or destroys itself trying. Earth may have hosted multiple attempts at this intelligence spiral, with each attempt reaching different levels before terminating. Which brings us to the most unsettling question of all. We can only find evidence that we know how to look for. Our scientific instruments and analytical methods are designed to detect signatures and patterns that we understand. We search for chemical traces that resemble our industrial processes. We look for artifacts that match our engineering approaches. We identify environmental damage that follows patterns similar to our current impacts. But a truly advanced civilization might develop technologies that are completely different from ours. They might use energy sources that leave no chemical signatures. They might build with materials that integrate seamlessly with natural systems. They might solve the same problems we face using methods that are invisible to our detection techniques. This creates what philosophers call the detection bias problem. We are looking for civilizations that think and build like us, but missing civilizations that think and build differently. Our search methods are like flashlights that only illuminate objects similar to things we already know. Think of our detection methods like archaeologists using metal detectors to find ancient artifacts. They will find every metal object in the ground, but they will completely miss wooden tools, fabric clothing, and organic technologies that might have been far more important to the original civilization. Advanced civilizations might deliberately minimize their environmental impact to avoid the resource depletion and pollution problems that destroyed their predecessors. They might develop sustainable technologies that work with natural systems instead of against them. Such civilizations could exist all around us, having learned to live in harmony with planetary systems in ways that make them essentially invisible to our current detection methods. Which raises the final, most important question. 50 million years from now, what traces of our civilization will remain? Future geologists will find a thin layer of unusual chemistry in sediment cores from the early 21st century. They will detect plastic molecular fragments, artificial isotopes from nuclear testing, and carbon signatures from fossil fuel burning. They will discover mass extinction patterns, ocean acidification, chemistry, and metal distributions that clearly indicate technological activity. But will they understand what we were really like? Will they recognize our art, our literature, our dreams, our struggles to balance technological power with wisdom? Or will they simply catalogue our chemical signatures as evidence that another intelligence briefly altered planetary chemistry before disappearing? The Silurian hypothesis forces us to confront our own impermanence. We are not the permanent masters of Earth. We are temporary custodians of a planet that has hosted intelligence before and will likely host intelligence again. Our entire civilization is just one brief chapter in a much longer story. Think of Earth as an ancient library where countless civilizations have written their stories. Most of those stories have faded to illegible traces, detectable only through sophisticated analysis of chemical ink stains and paper degradation patterns. We are currently writing our own story in this cosmic library. The question is not whether our story will eventually fade like all the others. The question is what message we want to leave for the civilizations that come after us. Will they find evidence of a species that learned to live sustainably with planetary systems? Or will they find just another set of chemical signatures indicating brief technological brilliance followed by environmental collapse? The choice is still ours to make. But the geological evidence suggests we may not be the first civilization to face this choice, and we probably will not be the last.